Hello, my name is David Loveday, and I'm going to be presenting my final project for DS7335 Machine Learning 2 for the summer of 2022 term. And the topic we're going to be talking about today is meta learning, and sort of more specifically in the context of small data. So just a brief point about the motivation here. In my day-to-day life, I'm a geologist who works in the energy business. I'm often confronted with very, very small data sets in which we're asked to make some very big decisions from. And so when I had set out to do this project, I had wanted to do a more generalized, strategies for working with small data. Quickly found that there are no easy solutions. There's no magic bullets that will help you to build high quality predictive models for small data sets. But one thing that did emerge is this kind of hot topic right now in meta learning, and this is largely driven by research that's being done in the computer vision space, where folks are interested in building these classification algorithms, especially with image data, where you're able to take very few examples and build some high performing models. Essentially you need things to learn very quickly with kind of minimal input. And a lot of authors are finding success or see meta learning as probably the future of this space. So just to give a kind of very brief definition of small data, in sort of the world I live in, we're doing a lot more regression work than classification. And what I'm finding is there's no consensus in the literature about what is small data, but I do hear numbers thrown around of 150 to 200 rows. It very much depends upon what industry you're in. If you think of all the industries such as healthcare or energy, like sort of the subfield I'm in, stuff where you have very expensive data points to collect, right? So you only have a handful because they're very expensive or very difficult to record. But when you get into kind of the computer vision space, now they're talking about small data sets being on the order of 5 or 6 or handfuls of data examples. And two, they're also confront the problem where there may be not full representations of all classes in your data sets too. So in your handful of data points, you maybe have 3 or 4 different classes. But really what you're after is an algorithm that can identify many kind of novel classes, even outside of the examples. So the biggest problem when dealing with small data, and you'll find this consistently in some kind of very loud recommendations or warnings, I guess, is that it's very easy to overfit. And so you always need to be using conservative sort of bounds and parameters when you're working with small data. Otherwise, you will you very much run the risk of overfitting. So with that in mind, I've put this table out here, and this was borrowed from a couple of different authors, but there's kind of 3 different, let's call them flavors of issues that you run into when working with small data. You have the lack of generalization, right, where you just don't have enough data points to really using kind of conventional tools to come up with high performing models. You also have often it depends what the problem is, but you have the issues with imbalance. And then you get into the kind of third topic there is the difficulties in optimization. And this is where we're going to be spending most of the time. The shapes on the right-hand side of the page here are just what I've gathered, and certainly you're welcome to, some quick searches through the literature. You'll find a lot of discussions on all these different methods to address each of these specific problems. But we're going to be dealing with this problem where it's kind of, most of the vast majority of the literature is focused on computer vision, sort of one-shot, few-shot problems. And we hear there's a lot of interesting research that's being done on transfer learning, as well as actually reducing the problem. And we'll touch on those a little bit later. But I'm gonna focus here on meta learning just because I find it very fascinating. I'm not sure how much applicability it has to my problems that I confront on a daily basis, but it is quite fascinating. And it in a way, it's kind of an abstract concept, but we'll go through some specific implementations. It can incorporate basically everything that you see here above it. It certainly has its roots in transfer learning, where you're learning from past experience and then applying it to as new data points become available. And it certainly can incorporate anything that you see, all of these methods that you see in the data imbalance and Lacquer generalization. So let's I think first step would be let's define exactly what is meta learning. I think that by far what you see in every paper that's been published on the topic, someone says or opens with it's a learning to learn strategy, right? Which, okay, that's I've heard that before. It's slightly abstract. So how does this kind of apply? How can we make this more concrete? And we find the bridge being there's many strong parallels and overlaps with those researchers who are studying cognitive behavior in humans and animals. And it's very interesting, and we'll go through kind of a key paper that was published in Science that they actually sort of bridge this gap and explain how they distill sort of all the studies in cognitive behavior and then draw the parallels and the extrapolations how you can bring this into the machine learning space. So I guess one way to make this a little bit more concrete is to actually define meta learning. So if you think about this in machine learning, we think of just a conventional machine learning algorithm as learning. It builds up its knowledge over multiple predictions of data instances, right? So we feed these inputs to a model, it crunches the numbers, and then it learns things from them and spits it out. Well, in meta learning, what we're doing is we're considering an algorithm as being an instance. So what you need to build these meta learning routines is you actually need a suite or a portfolio of conventional algorithms that you're actually optimizing the algorithm rather than optimizing the model, right? So we'll make this a little bit clearer as we go on here, but I just, one familiar example, and this kind of helped me to bridge it, up to this point in our studies as students, we've been exposed to, hyperparameter optimization via, traditionally it's kind of like grid search, but there's other kind of random search methods that you can optimize your hyperparameters, and this is in effect a sort of a meta learning exercise where we are, rather than optimizing the model based on our instances, we're actually optimizing the parameters, the hyperparameters of the algorithm, with some sort of loss function and some scoring metric in mind, right? So I always keep coming back to this because I'm exposed to it previously through our studies here, and I understand it. But what's really cool about meta learning, and again we'll dive more into it, is that it has a lot of flexibility. So you're not necessarily constrained to just hyperparameter optimization. So this is a handy graphic that I have borrowed, and it gives a very good general sort of structure of the most, the typical or by far the most common meta learning sort of architecture is what they call bi-level optimization, where you essentially have an inner base learning portfolio of tasks, and these tend to be just kind of conventional algorithms, which you build up a suite of these, a portfolio, right? And then you consider this as your inner or base learning tasks. And then you have an outer loop. So this is all embedded inside of an outer meta learning loop, where you through your meta loss functions, your meta gradient, your meta optimizer, you are optimizing these things on the fly through your outer sort of loop to build up your meta learning experience, which then you will optimize as if you're able to get more data points, right? So you're, you know, this graphic, this comes from some guys at these Fast Forward Labs who have a great white paper which talk a lot about few shot learning. So, you know, this works in the exact same way where we're using tests and training sets, right, to evaluate how our models are performing. And then, you know, the outer loop is kind of optimizing your parameters, and this is using neural networks, right? Though you're not constrained to just simply neural networks, but you're optimizing all of these nets as you go, right? Your suite of you know, your suite of inner learning tasks are being optimized by this outer learner. So we'll come back to this in a second, but you know, I put together this graphic here, and I think it is helpful for understanding how meta learning kind of fits into the context of machine learning and its sort of historical development. I borrowed the base, you know, image here from a paper, and then I've by hand annotated on here this human cognitive learning band, and essentially what we're trying to emphasize here is that conventional machine learning was largely driven by, you know, these hand engineered features, and really probably more of it, the value was in just, you know, the automation, the ability to just turn through large data sets quickly that it would be difficult for humans to learn. But what we see is that out of the gate, with very small amounts of data, human cognitive learning has a distinct advantage. We're able to quickly, as humans, or, you know, just kind of, you know, animals in general, are able to recognize patterns, you know, through, you know, placed into our, you know, our neural hardware by nature and evolution, that we have a distinct advantage in the environment of small amounts of data. And what we're finding is that, you know, with just few examples, human cognitive learning, you know, beats conventional ML for sure, and then deep learning as well. Though with more and more data, deep learning does kind of overtake, you know, the human cognitive learning fairly quickly. But where we're focused here, and I've drawn it, you know, with these arrows, is like this is the region of study where authors are doing much research on how do we bridge this gap here, where we come in with, you know, prior knowledge, you know, that we have, you know, via transfer learning, or do we warm start some of our algorithms to bridge this gap where we're getting better and better performance, more of that mimicking human cognitive learning, with in the environment, or this, you know, situation of having small amounts of data. So, you know, I found this every paper, modern paper that you find on meta learning in some way, either directly or indirectly, cites this paper that was published in Science in 2015. Now, meta learning was certainly being studied, and you know, people were working on these problems before this paper was published. But I think this paper just does such an excellent job of describing, you know, the understanding that you know, biology and physicians have made in how human cognitive brain function works. That these guys basically wrote this paper that mirrors or explains how this you know, human neural, the mechanisms are what are the analogs, or how are these working in the machine learning space. And so what we're finding, or what these authors are concluding, is that, you know, that through, you know, evolution, we have prior knowledge basically built into our brains, generation to generation. In some ways you can think of these as instincts, you know, for some like lower order species, you know, who are reacting 100% via instincts. This is past prior knowledge. That's how we need to think of this. And we actually have started to borrow some terms from cognitive science, and applying it to machine learning. So though now what we're talking, so I think everybody can understand, okay, we have some hard built-in knowledge, but we have also observed that we have an ability to learn based on, you know, leveraging some of this prior knowledge, which is hardwired in, that we're able to quickly incorporate new data, and we're able to expand this prior knowledge and or learn skills pretty quickly. So these authors have done an excellent job, and they describe the human cognitive system as being basically a system of Bayesian inference programs, meaning that human cognitive thought can be thought of as just these small, sort of very kind of focused programs of Bayesian inference. So basically, think probabilities, where sort of if then, and that our brains build up, take all of these little pieces and sort of, build on them, they add them together, they structure them, they build this whole architecture of these kind of smaller modules, and that, they're able to, build these in machine learning space, such that we're able to kind of mimic how human cognitive thought and behavior works, right? And I've just included this snapshot here to show that, they did kind of a test case where it was an image classification problem that they presented to humans, who were able to learn very quickly with small amounts of examples presented. But then, they, in this red bar here, they built a similar lookalike model that actually achieved results kind of on the order, or maybe even better than what the human test subjects were able to deliver. But all that being said, what we in practice, Bayesian machine learning algorithms, which use deep neural networks, are very computationally expensive, to the point of being kind of realistic for practical use. And this is where machine or meta learning kind of comes into play. And so if, again, we think of, and to draw the parallels here to biology, we think of these tasks as being these kind of conventional machine learning algorithms, where we have initialization models, parameters, and you think of these kind of as like the primitives, right? Which is a term that the authors in that science paper use, and that we can think of this portfolio of tasks as that is the prior knowledge, right? Or we think of these tasks then as being our actual input data set. Those are our instances. And so, in application and actually deploying meta learning in the field, what we do is we take, in our kind of cross-validation methods, we actually we sample our task set, our portfolio of tasks, and we, break them up into what we call the training and the test. And in meta learning jargon, they call these things support and then query tasks. And then we simply train our meta learning algorithm on these support tests, and then we, basically evaluate the performance. And then we go and iteratively make optimizations, and we test changes in the meta learning parameters that then, spill into and inform and guide the inner, so the tasks, the conventional algorithms. And we look at loss functions, we look at meta loss functions, and then, are able to build up our knowledge base. Basically, our knowledge base is these meta learning parameters, or optimized parameters. So just very quickly show you the derivation, because actually I think it's pretty straightforward and helpful here. So first, if we think of how the inner, just kind of like how do inner learning or conventional based learners work. First you think of your data set as just, in this case, let's just make it simple. We'll call it XY pairs, right? And we can train a model, right? A function F, which is parameterized by our parameters, theta, and we output a prediction, right? And our end goal is we want to find the optimal hyperparameters, of data, such that it minimizes the loss function. And so here we're showing theta star is basically the minimum of our loss function, where L is our loss function, and the inputs to our loss function are the data theta, and then the actual model, which is the lowercase omega there. The W always, I forget that's it's confusing, but that's the lowercase omega. So what we're doing with conventional, these inner base learners, is that we optimize basically from scratch for every problem that we're, the model's pre-specified. And often, when we're not, using hyperparameter optimization, remember that's a meta-learning process. We usually give it kind of static properties when we build our models, right? But what these researchers are asking is, we know how important these hyperparameters are, and we can see performance dramatically affected by just small changes in these hyperparameters. So how do we use these and how do we look at kind of changes in the cause-effect relationship of changing our hyperparameters to actually optimize some of the performance of these inner-base learners? So now if we think we'll step out to the outer loop. So let's now consider a task as being comprised of a data set and then its associated loss function, right? And now we would say that our learning process, or our meta-learning process, is where we want to minimize the loss for a task, right? And measure the performance, right, via whatever metric we would like. And we would optimize these in hyperparameters, or these whatever input parameters we'd like, and we called it the final sort of minimization, the suite of parameters that give us the minimized loss. We call this as a cross-task knowledge or meta knowledge. So, in very same way that we would train conventional parameters, we actually, use our training and our test sets, or our query and our source and our query data sets here. And really the training step is we want to find the optimized model given the source, the optimized meta learning, right? Given our source data set. And that's what we're seeing in equation 7 here, is we're actually looking to maximize the probability, right, of encountering meta knowledge given our source data set. And when we're testing it, we're finding the optimal parameters of a model given the meta knowledge. So we now apply those learned parameters to our training and our test sets here. And what's so interesting, what I find so interesting, and why I've been kind of fascinated with this meta learning, is that again, our example was where we're optimizing hyperparameters, but we'll go into this more in the different kind of flavors and different ways you can but this meta knowledge is very flexible, and you can use there's kind of no limit to the different sort of things you can optimize for. We can think of this meta knowledge as being an estimate of initial parameters, so we're kind of warm starting models, or we can think of it as an entire learning model or an optimization strategy just in general. So one kind of the last step here, and this is where we're going to bridge to that figure we showed before. This is just kind of emphasizing the bi-level architecture. As we said, we have this meta training step, so that's our lowercase omega star. But here now we want to cast the meta training step as a hierarchical bi-level optimization, where this loss function, this meta loss function, actually contains then within it the loss function of the specific task, right? Now that specific task loss function becomes a constraint then within the loss function of your meta optimizer. So we, they speak of this as being sort of asymmetrical, right? Where the inner level optimization is conditional on the learning strategy defined by the outer layer, but can't actually change, right, your meta knowledge during its training, right? And so, I'm going to hammer this over and over again, but the greatest strength, and it's a tiny bit abstract, but there's a complete flexibility in whatever it is we want to optimize on, right? Again, we use the hyperparameter as an example over and over, but we're not constrained to that. We could use things like regularization strength, or we could actually even use a different loss functions, or the parameterization of a loss function as your meta learner, right? But here's the problem, like with anything where we have a lot of strength, there's also the danger. And meta overfitting is definitely an issue, and I see folks for all of the time spent talking about the advantages of it, there's an equal amount, and again I'm talking about what I've seen in the literature, there's an equal amount talking about some of the dangers and how you can definitely see meta overfitting as well. So there's one paper in particular who did an excellent job of summarizing what are the different kind of things that were, or representations, that's the term they use, that we can, what are the different sort of meta knowledge things that we can learn. And so the first question when you're designing, the architecture of your meta learner, first things we have to ask is what exactly is it that we want to do? And we'll go, next slide, we'll go in much more detail on that first point there. But the second is like, how do we do it? And what are we going to use as a meta learner? And, some of these things those are certainly related. Representation and optimizer, you would make a sort of best fit. Your optimizer would best fit whatever you decide is your representation. Right. But then your objective is needs to be clearly defined or thought through, right, before implementation. And we want to define this, and it's very important to define this because it will guide how we choose our meta objective loss function, and how do the data and updates and knowledge flow between the inner and the outer loop. Again, there's a couple of I found a couple of interesting examples where they're talking about, by far, sorry, to back up, the bi-level optimization is by far the most sort of prevalent in the literature, but there are some feed forward designs that I've seen allusions to, but they all rely on kind of this classical sort of validation, validation test set. So it's, this cross validation is still equally as important in the meta learning space as it is in the conventional learning space. So to dive a little bit more into our meta representation, right? And this is kind of this is a very big, kind of the most important step when we're considering meta learning. We have to decide what exactly is it, what do we want to learn, or, what do we want our meta learner to, focus on? And so and then also, conversely, whatever we decide to learn, we are making a judgment then on what will be fixed as well. So all of these examples that you see underlying the meta representation are, there's examples in the literature of where these have been published and discussed and applied. I'm going to focus just on a couple of them because, again, we've talked a lot about, how this is being, the ground is being broken, and most of the research is focused on computer vision problems, mainly, one-shot, few-shot learning. But we do have a couple, I've just highlighted in blue there, a couple of different examples where we've got, applications of meta learning in different sort of spaces. So, we can do things like data augmentation seems to be a pretty popular meta learning optimizer, where mainly this is looking at things like noise or image distortion, right? Where you're actually optimizing the best approach to distorting your data, right? To actually artificially increase it. So sort of, this is where we're taking, if we only have a handful of representations or informations, we can actually introduce some noise or stretch, squeeze, especially images, and distort our data to actually artificially increase our data set. And this is, you can design a meta learner which will actually optimize what is the best, sort of use, or what's the best stretching and squeezing to get the most out of your model. And then in the same way, where there's transfer learning, another very hot topic right now. This is coming back to maybe some of the things that we were talking about from that science paper, where modularity is a big issue, where we're actually learning kind of smaller modules or smaller bricks, right, that we can stack together rather than just approaching a giant complex problem. We can actually break it into different pieces. And there's some great examples of where transfer learning, we're actually optimizing how all of those sort of modules kind of fit together, right? And then finally, is, reinforcement learning, This is kind of aside from computer vision, there's a lot of discussion here about the applications of meta learning and reinforcement learning. And this is kind of driven by that, that, as we have an agent that's acting, right? And then, this becomes a series problem or a sequence problem where, the data distributions change based on whatever the prior move was made by an agent. A lot of the kind of historical applications of reinforcement learning, we had to do a lot of manual kind of handcrafting with the heuristics. But there's some really cool research being done where they can, where actually your meta learner explicitly is defining an exploration strategy, or they call it a curiosity function. And so then rather than learning to learn, your model is optimizing and learning, iteratively learning how to explore, which I thought was really fascinating. There's a lot going on here on this slide, but I've just kind of broken down some of the, here's some specific examples of applications and some of the derivative work that have come from meta learning. So again, most of these are kind of weighted on computer vision problems, but there's three big buckets that I found, and you can break these into a discussion on prior knowledge about similarities. So where we're introducing or what we're optimizing for are the characteristics of your instances within your inner loops, that what are the similarities between like data points, right? And that becomes in itself just what your meta learner is focusing on. There's the second bucket there is where you have your prior knowledge about learning, all right? So this is kind of, I think, where a lot of our hyperparameter optimization sort of falls in this bucket. And this is also, if you're doing anything in a temporal sense, would fall into this knowledge about learning bucket. And then finally, you actually have a knowledge about the data, right? And this is prior knowledge about the data, that is. And this is where you're looking at architecture, and you're seeking to characterize a generative model of all possible classes with the least number of parameters, right? And or we're going to exploit, and this is where transfer learning kind of comes in. This is, or you're going to exploit things that we've learned in different tasks, and that we're, looking to kind of, let's call it warm start, warm start our, a new model. And or this is also where we introduce some of those things we were talking about with data augmentation. So, in conclusion, here's kind of the last things I want to talk about. There's, I want to just do a step through of a very popular and kind of like the most common actually implementation that I saw in the literature. It's good too, because you'll hear in a second why I think it's really illustrative for understanding, sort of how we actually apply this stuff out in the field. And this is, we'll walk through what's being called MAML, very, very creatively called MAML, and it stands for Model Agnostic Meta Learning. And so this is something that, the authors have shown success using this in kind of, the computer vision world, but also we're seeing this in reinforcement learning, and as well as just kind of regression problems too. And we'll step through kind of how you augment and adapt for each of those different scenarios. So the way this strategy, we'll call it, works is that, we're looking, so we have our portfolio of tasks, we'll call it P of T. And so rather than, what we're looking for are the best parameters that give us the best result for all tasks, rather than looking for just those that, you can imagine that just focusing on a single task will have its own unique set of, optimal parameters, which may not be as applicable to the next task. So what we're looking for, how this algorithm works, is it's looking for sort of what's the best suite of parameters that give us the, a higher performance across the board, right? It's kind of an optimization of an optimization, right? And in effect, what we're doing is we're looking at how sensitive our loss function is to changes in the task, such that, these small changes in our parameters will produce larger improvements on the loss function, right? So here we're focused, our scoring metric is the change in loss function through each iteration. So here's a set of parameters. We get a L sub 1, and then we run it again, another iteration, we get L sub 2. What's the delta between those? And those will actually, if you're looking at the bottle diagram there, so we're looking at our sort of how our parameters that we're supplying to the inner learners are evolving. And we're seeing, we're basically making judgments on how to adapt those and change those based on the change in the loss function. So, to go through some pseudocode here, I thought this was pretty insightful and helpful. So, I think we're going to look at this from kind of a K-shot. Let's think of it as a few shot learning setting, where we're drawing a task from our suite of tasks, and we're only using, a handful of samples. It's called 3 or 4 samples, drawing from our distribution of instances or observations, and then we build up a corresponding loss function that is relevant to a particular task, right? And then as we train a model, we take that model and then we test it on all the other tasks in our portfolio set, and we look at how all of each of their own independent kind of test error rates, in the context of these new suite of parameters, we look how that changes, right? And then we look at the delta, right? The change or the difference between our old loss function error rate and then our new loss function. And then we will use that to inform how we're updating the parameters, and we spit out a new set of, here's our high scoring parameters or minimum losses. And then we, iterate again through that, looking, until we hit some sort of, minimum. Again, it depends on our gradient function, and there's a whole suite of different ones that are, folks are finding, useful and high performing in the meta learning space. So very powerful, because this is, can be done and adapted for virtually any situation, from computer vision to kind of regression. And then, we'll talk about, how do we adapt this for, reinforcement learning and then regression. And so, if you think about what's our goal in regression, we want to make predictions on continuous valid functions from just a few data points, and using conventional methods, we know how dangerous this can be. So our loss function now usually corresponds to the mean squared error or something similar. And here, it's not a sequence problem, so there's not a temporal component. So our horizon basically goes to 1, the constant. And really the only adaptation we're making is from the sort of the K-shot learning is that we're sampling our data points. We're again evaluating. We're evaluating the change in loss versus our previous set of assumptions, and then we're updating those parameters. So very straightforward. I mean, really no major structural changes here to get this appropriate for a regression setting. And the same goes in terms of your reinforcement learning. Now, again, we said one of the challenges in reinforcement learning is that your data distribution changes with each move that you make. Every move that your agent makes, your new data distributions change. And so to accommodate that, the task that we basically these problems become Markov decision processes, where we allow the learner to query a limited sample trajectories, right? And then we evaluate each of these different trajectories based on our parameters that we gave it for exploring. And then we look at the loss function. It's very straightforward, really, really fascinating. So in conclusion here, and I just want to point out some of these references. These are excellent references. I really enjoyed this project, and I see meta learning has the potential to be sort of the next gen. We went from conventional machine learning to neural networks or deep learning, and meta learning may be the true next evolution of machine learning, and really we focused on its applications of small data, but there's plenty of discussion saying how can this or what kind of performance improvements should we see even in the environments of big data too. And there's very good reasons to believe that we should see even increased performance, as we get in larger and larger data sets. Now, the challenge will be just sort of computational cost, right? They're kind of very computationally intensive, which is why they work so well at the sort of small data scale. So thank you for your time, and I encourage you to explore a lot of these papers. In fact, I think every data scientist should read this science paper here called Human Level Concept Learning Through Probabilistic Program Induction. Excellent read, fascinating, whether you're in data science or not. It's just a very fascinating read on how the human brain works. So thank you.